Okay, hello all and welcome to this video where we're going to look at the product rule and quotient rule. These are two rules that help us with differentiation. So let's jump straight into it, and with both of these rules I'm going to be jumping between function notation and, for lack of a better term, what I'm going to call Leibniz notation. Most of the time, personally, I have a preference for this Leibniz notation. I get slightly less confused and it's a little bit more compressed. So that's what I'll lean towards myself personally when I go through the examples, but I will try and use function notation where I can. Right, so let's look straight at the product rule. So the product rule is used when we have the product of two functions and we want to try and differentiate it. So let's say we have capital F of x, and that's what we're going to use to show this combined function, is equal to some small f of x multiplied by g of x. Then if the derivative of both these individual functions that are multiplied together, if the derivative of those exist, then the derivative of the whole function is equal to f of x times by the derivative of the other part, okay, the other function, then times by the original g of x times by the derivative of that. Okay, so f of x times by g dash of x plus g of x times by f dash of x. It looks a little complex there, but when we look at it in Leibniz notation, I think it looks quite simple, really. If we have, again, the product of two functions that we call u and v, and u and v both have derivatives, then the actual derivative of the overall function, y, is equal to u times by v dash plus v times by u dash. So it's sort of like the chain rule where we're combining a couple things together, but it's pretty straightforward. So let's jump straight into it. Some couple of worked examples, and the big trick with this is, or just main skill, is making sure we separate the functions, the two functions that are multiplied together, and identify that it is a product rule. So for example, if we have x squared sine 2x, okay, f of x is equal to x squared sine 2x, we can recognize that that is actually x squared times by sine 2x. So we have the product of two functions and the derivative of both of those exist. So we let the left-hand function, we call that f of x, and then we let the right-hand function, we're going to call that g of x. Just state them separately, and then we're going to find the derivative of each of them. So the derivative of x squared is 2x. The derivative of sine 2x is 2 cos 2x. We know them from our shortcut rules. So now that we have all that, we have f of x, we have g of x, we have f dash of x, and we have g dash of x, well, the derivative is the special combination of them, where let me use some colors here, we've got f of x and f dash of x over there. We've got g dash of x and g of x there. So it's really combining one original with the other derivative and then taking the other original and combining it with the other derivative. So we can see that these two end up being multiplied together and these two expressions end up being multiplied together. Multiply them together and then simplify where possible, and we get this derivative here. Now, it's not a really nice looking expression, but it's an expression nonetheless, and it is the derivative, and we can use that in applied problems. We have the exact same example here on the right hand side. Same thing, we're just using slightly different notation. We let u equal to x squared, which is the left hand function. We let v equal to the right hand function, and same thing, we state the derivative of both of those, and then we do the combination. We combine one original with the other's derivative, we combine one original with the other expression's derivative, and let me see, let's use some color here. So the one's connected by that red arrow there on the left, the one's connected by the green arrow there on the right, and same thing, we get the same answer. The handy thing with the product rule is that the order doesn't actually really matter. As long as you're taking one original other derivative and then switch and combine those two with an addition sign, that's our product rule, and it goes together really easy. So let's jump straight into an example, and this was from 2017 VCAR Exam 1, so this is tech free. Get rid of the eraser. So we have y is equal to x log e to the 3x, find dy dx. So it's a y equals, it's not using function notation. Like I said, I'm going to use Leibniz where possible, so I'm going to let, if I look at the function, I can see it is the product of those two expressions or those two terms. So I'm going to let u equal to x, and I'm going to let v equal to log e to the 3x. Okay, so there's my two separate expressions. I'm going to differentiate both of them. So u dash, the derivative of x is just 1, and v dash, the derivative of log e of 3x, is just 1 on x. We could, and that's just knowing a shortcut rule, but we could use the chain rule for this. Bring this out separately and go, okay, I'm going to let the 3x inside be something, apply the chain rule, combine them together with the chain rule, and then it turns out the 3's cancel out, because what you actually get using the chain rule is 3 on 3x. And the 3's cancel to just give us 1 on x, if you remember the shortcut. But you can use the chain rule for sure. So from there, we can say it follows on that dy dx is equal to u v dash plus v u dash. Okay, just taking an original, combine it with the other derivative, take the other original, combine it with the other derivative. And so I'm going to multiply these together. So u is x, v dash is 1 on x, plus v is log e to the 3x, times by u dash, which is 1. So we get x on x, which is 1, plus log e to the 3x. So there's our derivative of that function. And that's pretty powerful. Like, I can't understate how powerful this rule is at finding derivatives. Anytime we have the product of two functions where both functions are differentiable, we can use this product rule. So yeah, out of time. Okay, here's another quite long example. I'll talk about it for a little bit, and then you can pause and copy down if you so want. But same thing, it's just noticing that we have, there's one expression multiplied by another expression. Okay, so straight away I'm thinking, as it says here, let u equal to e to the power of 3x, let v equal to the square root of x squared minus 1. So there are two expressions that are multiplied together, so we have to use the product rule. The trick with this is then looking at this v is equal to x squared minus 1, and as it says down here, finding the derivative of that is we have to use the chain rule. Okay, so if we go separately, I'm just going to say let g equal to, well, we've got v, let's use v. Got v is equal to x squared minus 1. I'm going to let, let's say, g equal to x squared minus 1. So we've now got v is equal to the square root of g, which we can also say is g to the power of half. Okay, and we've got g over there. So dv dx, which is the derivative of this, is going to be equal to dv dg times by dg dx. That's our chain rule for this one. So it's using a couple different variables to describe it, but it's still the chain rule. Is we want the derivative of the original, and we get that by the derivative of the simplified version multiplied by what's going to be the derivative of what's inside that composite function. So let's finish this off quickly. So we know that from here, v dash is going to be multiplied by the power, so we get half g, take 1 from the power, to the negative half, and g dash is equal to 2x. So if we combine those, we get half g to the negative half times by 2x, which will be 2x on 2, and because g to the power of negative half, I'm going to bring that down into the denominator and use my index laws. That would be g to the half, and if we substitute in what g was way back here at the start, we get this final expression, especially once we cancel out the 2's. We're left with that x on top, and then substituting g, x squared minus 1 to the half, which is the square root. So this is actually likely, even though this last example wasn't chain rule, but the recent trend lately in exams is, this was just a nice simple product rule, but even here you could have been using the chain rule to calculate this. The trend in the methods exams is that there's a product rule or a quotient rule, but one of the bits inside it, like this one here, you have to use the chain rule. So you have to think, okay, overall I've got a product rule problem, but inside this product rule problem, I need to break out and do a chain rule for some small part of it. And that's a very common theme in the methods exam. So being really consistent with your notation, being really clear with what variables you're picking, especially once you come over here and do the chain rule, will be really helpful. Okay, so let's do one more quick example, which ties straight into this. So straight away, I'm going to let u equal to 3x squared is my left expression. I'm going to let v equal to x cubed plus 2x all squared. That's my right-hand expression. They're multiplied together. Now, with this one, I could expand everything, get it in polynomial form, and then differentiate it. But let's have a go using the product rule instead. So straight away, nice and easy, is u dash is going to be equal to 6x. Now v dash, this is that example where, well, to differentiate that, we have to use the chain rule. There is the shortcut, which says that this is going to be, actually I'm going to avoid that at the moment. Let's just use the chain rule. So coming over this way, I'm going to let x cubed plus 2x, I'm going to let g equal to that. So g dash is equal to 3x squared plus 2. And from that, we've also gotten that v is equal to g squared, which is this bit here simplified just using putting g in it. So we get, change the notation just a little bit. This is dg dx, this is dv dg is going to be equal to 2g. So it follows on that v dash is equal to d g dx dv dg, which gives us, change the order, that for consistency's sake, normally do dv dg first, dg dx. Okay, so we get 2g bracket 3x squared plus 2, which is equal to 2, and g we said is x cubed plus 2x by 3x squared plus 2. Okay. So we have that. That's our derivative finally, so we can write this over here. 2 bracket x cubed plus 2x 3x squared plus 2, and now we can finally say, well, the derivative of this, which let's maybe say we're going to let y equal to that. So y dash is equal to u v dash plus v u dash. That's the product rule, which will be equal to 3x squared bracket 2 bracket, actually we don't need that first bracket, let's just put times 2 x cubed plus 2x bracket 3x squared plus 2 plus v, which is x cubed plus 2x all squared, times by u dash, which is 6x, which, let's simplify just a little bit, gives us 6x squared, x cubed plus 2x, 3x squared plus 2, plus 6x, x cubed plus 2x all squared. Again, still not nice, and if we expand this all out, we could get into polynomial form, but it's just showing that we can use the product rule. So we get to add the product rule to our differentiation tree now. So we are almost at the end. We've got one more thing to add, and that is the quotient rule. And we use the quotient rule, and this slide here is looking at it in function notation. We use the quotient rule when we have the quotient of two functions. When we have this situation here, f of x divided by g of x. Quotient means division. So when we have the division of two functions, this is the derivative. So if we look at the denominator, we get the denominator times by the derivative of the numerator, subtracting the numerator times by the derivative of the denominator, all divided by the denominator squared. Okay, so this rule is a little more complex, and order does matter, especially because this is subtraction. So it's the original denominator first. The rest of the numerator looks very similar to the product rule, but it's the original denominator first multiplied by the derivative numerator, subtract, blah, 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 blah. Okay. A little bit easier to read in Leibniz notation, I think. Okay, so same thing, original denominator times by derivative of numerator, so v dot u dash, take away u v dash all over v squared. And we have an example here. Okay, our numerator is e to the x, our denominator is e to the 3x minus 2. We find the derivative of both of those. Let's get a bit of colour for consistency's sake. Find the derivative of both of those, and then we just follow the rule, do the substitutions, and then simplify where possible. And we get this as our final derivative. Again, not very pretty looking, but extremely powerful. It allows us to find the derivative of the quotient of any two functions where both functions are differentiable. And the key thing to this too is also that when you square v, you don't actually get 0. Sometimes if you... Is there possible? Probably not. If v's not 0, then squaring it can't make it 0, I wouldn't expect. But there would then lead to some restrictions, like you can't have that denominator bit equal to 0, otherwise the derivative doesn't exist. But let's jump straight in and do a couple quick examples. So I'm going to let u, and we always let u be the numerator, as x squared, and v equal to x plus 3. So straight away u dash is 2x, and v dash is just 1. So follows on, and same thing, let's let that y equal to, so dy dx is equal to v u dash, take away u v dash, order is important, all divided by v squared. So we're going to get v is x plus 3 multiplied by u dash, which is 2x, take away u, which is x squared, multiplied by v dash, which is 1, all over x plus 3 squared, equals 2x squared plus, I'm just expanding the numerator now, plus 6x minus x squared, all over x plus 3 all squared, is equal to x squared plus 6x on x plus 3 all squared. And we could expand the denominator as well, maybe see if, or we could take out, see if we could write this as a difference of squares, take out a common factor and simplify, but we'll leave it for there. That's the main idea, is this sort of step up here, and then the rest is just substitution and basic algebra skills. Same thing for example 2. Let's let u equal to sine x and v equal to x minus 2. So u dash is cos x and v dash is 1. So, and let me just double check that that's not negative cos sine. What does the sine graph look like? It starts at 0, goes like that. So it goes positive first. Yeah, so that's, yes, that's right. So it follows on that dy dx is equal to v u dash take away u v dash all over v squared is equal to x minus 2 times by cos x take away u, which is sine x, times by 1 all over v squared. So that's x minus 2 all squared is equal to cos, let's just leave it as that's sort of written, x minus 2 by cos x minus sine x over x minus 2 all squared. And we'll leave it there. So that's quick examples using the quotient rule. Like I said in the previous section though, it is highly likely that one of these two terms you'll actually need to use the chain rule, not terms, expressions, so to say. Maybe u or v, you might have to use the chain rule to actually figure out the derivative of that individual expression separate to the quotient rule. So here's a really quick exam example. So same thing, it's from the 2017 exam 1. So we need to let f is equal to this function from x over x plus 2, differentiate f with respect to x. Key thing here is that it's a full function notation. 2 marks, so I'm going to be really careful and probably give my answer in full function notation as well. So I'm going to let, we didn't do this on the previous slide, did we? No, it's different. Okay, we're going to let u equal to x, v equal to x plus 2, u dash is 1, v dash is 1, so f dash of x using their notation is equal to vu dash minus, and did I use minus over there? Yes, I did. Minus u v dash on v squared is equal to, where's there? X plus 2 all times by 1 minus x times by 1 on x plus 2 all squared is equal to x plus 2 take away x on x plus 2 all squared is equal to 2 on x plus 2 all squared. So there's our derivative f dash of x. Now I'm going to, just because there was a domain given from -2 onwards, I'm going to also use that negative domain. So I'm going to say the answer, the derivative from -2, because our derivative should have the same domain because it's over the same x values. It's telling us the gradient of those x values. The range can of course change, but the domain should be the same. F inverse of x is equal to 2 on x plus 2 all squared. And that's it. Okay, so really simple using the quotient rule. Here's a proof of finding the derivative of tan theta. Now, I gave you the shortcut for that couple lessons ago, but if we let tan theta equal to sine theta over cos theta, you can then use the quotient rule, which shows here, doing some simplification, we get 1 on cos squared theta, which is defined as sec squared of theta. Yeah. So we've added the quotient rule, and that's it. That's our family of differentiation tree. So what have we got here? We've got polynomials, we've got rational powers, we have composite functions using the chain rule. Over here, we can do using index laws, we can do square roots. Where do I have square root? There's a version of square root. We can do a hyperbola, we can do a truncus, all using the power rule. We can now do composite functions, we can do product functions, and we can do quotient functions. And there was that shortcut around finding the derivative of the inverse a couple lessons ago. That's it for all rules that we need to know to differentiate. But there is still one more video looking at then when are actual functions differentiable. So that'll be next. Thanks, and as always, if you have any questions, post them below or shoot me an email.